Well, with an understanding of the igneous rocks, those that make up 80% of the crust, I thought what we'd do is to go to the other extreme and pick up the sedimentaries. Now, remember, the sedimentary rocks, volume-wise, don't really represent an awful lot, 5% of the entire crust. But I think one of the important things about the sedimentary rocks is they cover 75% of the land. Now, the significance of that is it means almost anywhere you travel in the world, I don't care where you go, chances are you're going to be surrounded by sedimentary rocks. So for that reason alone, I think people will know a little bit about them. But there are other importances to the sedimentary rocks too. And I'd like to just make a few comments, for example, about energy. Without getting too deeply into it, the energy of this country is dependent upon 70% upon petroleum, oil and gas, and over half of that is imported into the country. And all of that is used to make either diesel or gasoline. And the question is, where does it come from? Well, the source of it is actually marine plants, but once you make it, you have to store it somewhere. And where we store it are in rocks called reservoirs. Well, it just turns out that all of the really great reservoirs are sedimentary rocks. In particular, there are only two of any note, sandstones and limestone. So for that reason, I think they have some importance. If you're looking for oil and gas, you look for sandstones and limestones. Now, the second number two energy source in the country is coal, and coal represents about 20% of all the energy of this country. And those of you who live in coal country, like I do, you can just drive around and see that coal is intimately associated with a sedimentary rock. You drive down the road where I live, and you see sandstones and shales, there's a bed of coal. So the intimate relationship between the two is, I think, important. So there's your 20% of your energy. And in this country, 5% or thereabouts is uranium. Now, that sort of holds steady since 3 Mile Island, but the uranium we use comes from sedimentary rocks. In this country, most of our deposits of uranium come out of places like New Mexico, where it's in sandstones. So again, if you just look at the energy picture in this country, 95% of all the energy in this country is somehow related to sedimentary rocks. So even for that reason, I think we ought to take a look at it. But there's another reason, and I guess this is strictly a geological thing. To a geologist, it's nice to make money and all the other things, mining coal and things like that. But the importance to us as a science is the fact how it records history. When you get right down to it, the basis for geology to exist is to work out the history of the earth. That's what we want to do. What we would eventually like to have is a book called History of Earth, and open that book to any place on Earth. And in this book, it would record exactly what happened from day one until day now. And it turns out that almost all of the history of the Earth is recorded in sedimentary rocks. For example, picture how they're formed. They're laid down layer by layer by layer. That's one of the characteristics of sedimentary rocks. And the way we sort of look at it is each one of those layers is sort of like a page in a book. And there are things that are recorded and encapsulated in the rocks. It might be the composition of the rock. It might be sedimentary features that you see in the rock, like ripple marks or whatever. These are telling you something about what it was like there at the time that material was laid down. The best one, of course, are fossils. Most of the history of the Earth is recorded in sedimentary rocks in the form of fossils. And the reason why fossils are so good, for example, I think you know that with rare exceptions, every plant and animal has a very specific climate under which they will live. Temperature, precipitation, whatever. And you really can't get far out from that. A good example, for example, would be coral. In the case of coral, if you think what all the coral of the world is, all of it is really concentrated between the Tropic of Cancer and the Tropic of Capricorn. You can't get very far out of that belt and your corals die out. So every plant and every animal, with rare exception, is like that. Well, the fact of the matter is that modern paleontologists are really comparative anatomists. They know their animals and plants so well that when they look into the fossil record and they find a plant or an animal and they look at the various structures that are preserved, knowing what the structures do today in the plant or the animal, they assume that it did the same thing then. So using that, the paleontologists can today to tell you just about anything you want to know. They can tell you whether this place at that time was land or ocean bottom. If it's ocean bottom, they can tell you whether it's warm or cold. They can tell you something about the salinity. They can tell you something about the depth. It's really amazing what they can tell just from the fossils alone. Well, that's the importance for us. Every one of us is geologists. My goal as a geologist in a lifetime is simply to add just a little bit to that history book. Each one of us can add only a little, but that's the purpose I'm here for, is to add a little bit to the history of the Earth. So there's sort of a little background then of what sedimentary rocks are all about and why we study them. As a matter of fact, geology majors, I might point out, as an undergraduate major, they probably spend 75% of their time learning how to read that history in the sedimentary rocks. Now, on to what they are. By definition, a sedimentary rock is any rock formed from the products of weathering. Well, we're going to talk about weathering in another lecture, but just some basic ideas about what weathering is. Weathering, by definition, is any process whereby rocks out there are attacked physically and chemically and either ripped apart or decomposed. Let's take physical weathering first. This is a very, very simple process. We have processes that simply tear rocks into pieces. We simply refer to them, obviously, as rock fragments. And the very best of those processes would be the freezing and thawing of ice. So in temperate climates, for example, like where most of us live, I guess, freezing and thawing of ice is a very, very potent process. Why? Well, just think about it. When water turns into ice, there's an expansion of about 10%. Now, it doesn't sound like an awful lot, but if that water were being expanded, let's say, in a container that was sealed or closed somehow, the pressures that develop in there are going to be very, very high. I don't know exactly what it is. I looked it up one time. It's something over 1,000 pounds per square inch, which is just a big number until I point out that 30 pounds in your tires lifts your car off the road. So this is a potent force. So the idea is that freezing of water in a small crack, for example, makes the crack just a little bit bigger. And then when the thaw comes, the bigger crack now takes more water, and then when the next freeze comes, it expands even more. And so I think you can see going through this freeze-thaw cycle, the rock is progressively just literally ripped apart. And you can see the evidence for that, certainly in temperate climates like where we live. You drive down the road, especially in the springtime now, and that's where you see all the debris out on the roadway. Why? You've experienced many, many winters of freeze-thaw, and finally the spring comes, the final thaw comes, the rains come, the little bit of material that may be holding a rock in place up there on a hillside is removed, and down the rock comes. So that's the reason why most of the debris you see along the roadway is in the springtime. Oh, I know it can fall any time of the year, but most of it's in the springtime. So freeze-thaw, very, very potent. Call that frost wedging. The other thing, in other places, for example, let's say in the tropics, obviously you don't have freeze-thaw, but you have plants. And if I had to pick number 2 in terms of ripping rocks apart, I would pick plants, the roots of plants. The plant roots go down looking for something to eat. They get into little cracks and crevices in rocks. When they find their food, of course, they send it up to the main plant, and the main plant gets bigger. But as the main plant gets bigger, so does the root. And as the root grows in diameter, it, in turn, it imparts a lot of pressure within the crack, and pretty soon it'll rip rocks apart. I think you've all seen, for example, a sidewalk heaved up by a tree root going underneath. That's the very process we're talking about. So between those two, rocks are ripped apart, and one of the products of weathering then are simply rock fragments. Rock fragments are what they say they are. They're just bits and pieces of rock. The composition just depends upon what rock, obviously, was being ripped apart. Now, chemical weathering. This is sort of more dear to my heart, being a chemist at heart. Chemical weathering really involves only 2 major processes: oxidation and carbonation. Now, carbonation is the result of carbon dioxide, obviously oxygen. Oxidation is for oxygen. Now, here's the deal. When you think about rocks being exposed out there, we say they're exposed to the weather. Well, what they're really exposed to is water. They're exposed to rainwater. Think about rain falling through the atmosphere, for example. As it falls through, the atmosphere is 21% oxygen. It becomes oxygenated. Now, once the oxygen is dissolved in water, then it becomes a very active oxidizing agent. For example, gaseous oxygen is really not a very good oxidizing agent. At high temperatures it is, in a fire, in a acetylene torch perhaps, but not out here in the open. Thank God for that, because here we are carbon units, If it was a really good oxidizing agent in the gaseous form, we would simply be big puffs of carbon dioxide. So in the gaseous form, it is not a good oxidizing agent. Once you dissolve it in water, it becomes a very good oxidizing agent. So there's one of your agents of chemical weathering. The other one is carbon dioxide. Again, carbon dioxide is in the atmosphere, not very much of it. But the thing about carbon dioxide, it is very, very water soluble. That's the basis behind your favorite carbonated beverage, whatever it may be. Carbon dioxide is taken out of the atmosphere. It's also taken out of the ground, of course. That's another source of it. But what you make is carbonic acid. Now, carbonic acid is a very, very weak acid. It's so weak, for example, that you can drink it, and you do. You can take a shower in it, and you do. You wash your clothes in it, you do. The fact of the matter is that all water is really a dilute solution of carbonic acid. I always tell my students, carbonic acid in the air, it's been falling as acid rain since the very first drop of rain fell. And of course, the acid rain we talk about today is a little bit stronger acids, but nevertheless, all water is basically a solution of carbonic acid. So here's the way it works. Think now of those 9 silicate minerals we talked about. Over on one side of the little table was the ferromagnesians, remember, iron and magnesium. The oxygen now, the dissolved oxygen, about the only element in any of those things that really likes to oxidize is iron. The others can and will, of course, but iron really likes to oxidize. So picture, for example, any of those ferromag minerals, what's going to happen, water with dissolved oxygen is going to attack the ferromag minerals, take the iron out of the crystal structure. Now, once you start doing that, it's like taking bricks out of a wall. The rest of it's going to start collapsing after a while, and that's the beginning, you see. The iron is taken out. It's made into an iron oxide. In terms of how much it is, there's not much of it. It precipitates out as a solid we call hematite. Not much of it, but it's the coloring agent in most soils and rocks. You don't need an awful lot of coloring agent to make a rock color. A little drop of ink in a bucket goes a long ways, the adage I always use. So anyway, that would be the oxidation. Now, the carbonation, the carbonic acid attacks all the minerals you saw except for 2, olivine and quartz. They are converted into a very, very important silicate mineral, the clay minerals. A clay mineral is defined as a hydrous aluminum silicate. Now, the reason why olivine will not make clay minerals is because there's no aluminum in it. We'll hold on for a minute on quartz. Quartz is a very special mineral in its own. But all the other minerals you saw in that table of the major rock-forming silicates, all of them create clay minerals. I mean, have you ever wondered why there's so much dirt? I always allow my students one day to call it dirt. Then they got to start calling it soil. But the dirt, it covers everything. The reason why every major rock-forming mineral creates it. That's the reason why when you go out there, you don't see many rocks sticking out because they've been covered with soil, the main component of which are the clay minerals. So that's the number one product of chemical weathering, are clay minerals. The other one, think about quartz now. Quartz is an interesting thing. You have quartz in just about all of those minerals. Remember the felsic minerals. Take granite, for example. You can see the quartz in it. When everything else is taken out, the quartz is left behind. Why? It doesn't react with anything. It doesn't react with dissolved oxygen. Why? It's already an oxide. It's already SiO2. There's no such thing as SiO3, so you see you can't oxidize it any further. But as a chemist, here's what I find very interesting. It doesn't react with dissolved carbon dioxide either. It doesn't react with carbonic acid. There is no such thing as silicon carbonate or silicon bicarbonate. And I have asked a lot of my chemical friends that, why not? Why doesn't it react? And no one has ever been able to tell me why. There's something that prevents it from happening. You look in the Handbook of Chemistry and Physics for silicon carbonate or bicarbonate, it does not exist. So the end product then, here's what we have. In terms of products, of solid products, you have the clay minerals, a lot of them. You have quartz, quite a bit. And then you have a little bit of iron oxide, just enough to color things. Then we have the dissolved components. The carbonic acid then goes in and it picks up things. Remember all the alkalis and the alkaline earths? The sodium, calcium, potassium, magnesium. And it turns those into bicarbonates. And you'll remember, of course, from your basic chemistry, all bicarbonates are water soluble. Picked up, hauled off, where to? Eventually to the ocean. So there's a tremendous amount of these bicarbonates. And of the bicarbonates, the one that seems to be most abundant in water is the calcium bicarbonate, which we'll get to before we're done here. The other thing that's left now is a little bit of silica. Now, silica goes into solution in the form of what we call silicic acid. It's Si4 or H4SiO4. Silicic acid is a really, really weak acid. It's even weaker than carbonic acid. It doesn't dissociate at all. It doesn't produce any hydrogen ions. So it just goes into solution and is carried off, eventually where? To the ocean. And we're going to see that one come back before we're done here today, too. So here's what we have to work with in terms of the products of weathering. We got basically three solid products: clay minerals, quartz, and a little bit of iron oxide. In the way of dissolved stuff, we have the bicarbonates, largely calcium is the big one, and we have silicic acid. So that's what's going to be used now to create sedimentary rocks. Okay, now sedimentary rocks. We categorize them based upon whether they're made of the stuff that was originally solid or whether it was made of the stuff originally in solution into clastic and non-clastic. Clastic rocks are those rocks that are made from the solid products of weathering. So we're talking here the clay minerals, quartz, and that little bit of iron oxide. Now, there are a bunch of these clastic rocks, but I'm only going to talk about the two that are very, very most important. Just based upon what we have said, it looks like whatever rock forms from the clay minerals is going to be the most abundant, and it is. The rock that forms from the clay minerals is we call shale. Now, you know what shales are. It's a very, very common sedimentary rock. As a matter of fact, 70% of all the sedimentary rocks are shales. What is it made from? Clay minerals. What does it look like when before it's made into a sedimentary rock? It looks like mud, because that's what mud is. Think about a flood. A stream goes over bank. The stuff that's in suspension are the clay minerals. That's what makes streams murky and not being able to see the bottom. That stuff floods out onto the floodplain, and that's where it's deposited. So after a flood, those of you who have experienced the flood, you get back after it's all done, and what's in your front yard or maybe in your house? Thick, sticky, gooey mud. That's what that is. Those are the clay minerals. So out there on, let's say, the floodplain of a stream, you have accumulated this mud, or maybe on the ocean bottom. That's where most of it accumulates, on the ocean bottom, because it's eventually hauled to the sea. So we have places where this mud accumulates. That stuff, before we're done, we'll show you how it happens, but that is converted into shale, the number one sedimentary rock. There are more shales than anything. Now, the next sedimentary rock of importance, as a matter of fact, the only other one in this group, would be sandstones. By definition, a sandstone is a rock made of sand-sized particles. Now, it just so happens, sand-sized particles, most of those are quartz. Think of the beach. You go to the beach and pick up some of that sand. What you're looking at is a handful of sand-sized quartz. The sand size refers to the fact that they average about the size of a pinhead. If you take that quartz from the beach or quartz from any place that's accumulating, perhaps in a desert, where it's not too terribly common, I might add, but if you take sand and turn it into a rock, it's going to be a sandstone. 20% of all sedimentary rocks are sandstones. Now, this is the interesting point. If you ask the average student, or perhaps the average person as you're driving along, which of those two rocks do you think would be most abundant, they almost invariably pick the sandstones. And I think the reason why is because you drive down the road, what you see sticking out in the cliffs are the sandstones, maybe the limestones. You don't pay attention to the shales. But the next time you drive down the road and you see a sandstone ledge sticking out, or perhaps a limestone ledge sticking out, look to see what's in between. And I think what you'll find is in between is going to be shales. And when you really get to looking at it, you're going to see that there's more shale than anything else. That's right, 70% shales, 20% sandstones. And the iron oxide is just a coloring agent. It's simply the thing that gives things red colors or sort of maroon colors or brown colors. It's the coloring agent in both sedimentary rocks and in soil. So that's the importance of that one. Now let's get on to the non-clastic. This is where the chemist comes out again. Non-clastic rocks. We're talking about rocks made from stuff that was once in solution. Now, right off the bat, if you're going to make something out of something that's in solution, the first thing you've got to do is get it out of solution to make it, okay? So the deal is that there are three basic categories of non-clastic rocks. And they really basically are how you go about getting the stuff that was in solution out of solution. And the three are chemical, biochemical, and evaporite. Now, the chemical implies that the process we're talking about is just going to be chemistry pure and simple. If you ask the chemist, how do you precipitate things out of solution, a chemist would say, well, you change either the physical properties that's in existence at the place or the chemical properties or both, and something will come out of solution. So we're going to see that. Now, biochemical means, it applies at least, that the chemistry is the same, and we'll see it really is the same. The bio is the part that's different, and what the bio implies, there's some organism involved. There's a plant involved. There's an animal involved. That's the only difference between the two. Now, the evaporite, what that's all about is that there are certain materials that go into solution, and once they go into solution, they really don't like to come out. For example, there are certain ions that are very, very water-soluble. Sulfate ions, for example. Once they go into solution, they just don't like to come out. You can precipitate them out chemically, but it's very, very difficult to do that. But the other one I'm going to talk about is the very common one we've been talking about, good old-fashioned halite, sodium chloride. Think about dissolving salt in a glass of water. As far as I know, there is no chemical reaction that you can do that would cause salt to precipitate from solution once it gets into solution. And as far as I know, there is no mechanism that any plant or any animal has to cause it to come out of solution. So how does it come out? Well, the only way you can get salt to precipitate out of solution is to get rid of the solution. So that's what evaporation's all about. If you take seawater, for example, and you evaporate it, you have to evaporate over 95% of it just to get it to start to precipitate. So you have to get rid of almost all of the water, but then it will. And so that's the reason why they're called evaporites, because there are certain minerals like that that are so water-soluble that you simply have to get rid of the water to get them out. Let's go back to the combination now of the chemical and biochemical. I want to treat these together because they really do go hand in hand. And the one I want to talk about is calcium carbonate. This, now remember, is the stuff of which limestones are made. So here's a little chemistry for you. The dissolving of calcium carbonate, the thing that does it is carbonic acid. And if you look at a reaction, calcium carbonate, the mineral, reacts with carbonic acid and goes into solution as the bicarbonate ion and the calcium ion. So anytime you see those little plus and minuses, you know it's in solution. So that's how it goes into solution. Now, here's the important thing. You're going to take my word for this because we don't have time to go into why. That reaction is favored by cold water. In other words, limestone calcite is more soluble in cold water than it is in warm water. Now, that's sort of different from every other thing, and like I say, we don't have time to really get into why, so you'll have to just take my word for it, but it is. In other words, if you go to for example, let's say you went to Nova Scotia or even the coast of California looking for shells along the beach. You won't find an awful lot of them. Why? Those shells are made of calcium carbonate. That water is very, very cold, and calcium carbonate dissolves in cold water. So that's the thing you have to remember. Now, if it dissolves in cold water, what happens in warm water? It precipitates, just chemically precipitates. Case in point, one of the places we take our students to study limestones and show them how they work is down to the Florida Keys. And if you ever want a neat place to go to the Florida Keys, and we take them down there, and we go back into Florida Bay. Now, Florida Bay is only about 10 feet deep on the average. The water is very, very warm as the result of that. So here we have an impoundment, a entrapment actually, because you got the Florida Keys trapping them to the south, and of course you have the mainland, and so it's sort of a wedged little basin there. Picture now water coming out of the deep part of the Gulf of Mexico. We're talking deep water. We're talking 12,000 feet. We're talking abyssal depths here. Very, very cold water. We have calcium ions and bicarbonate, lots of them in solution now, coming to the surface and being blown by the prevailing winds into Florida Bay. Once they get into Florida Bay, the temperature rises very quickly, and all of a sudden you have the chemically precipitation of calcium carbonate crystals. If you go back into Florida Bay, what you'll find back there is a thick, sticky, gooey mud, and if you take some of that, as we tell our students to do, put it under a microscope and look at it, what you see are tiny, tiny little crystals of calcium carbonate, strictly chemically precipitated. that would turn into a limestone. It would be a chemical limestone. All you have to do is walk across the street. We're talking to Florida Keys now. Right across the street is the open Gulf. The open Gulf is just normal marine water. It's normal temperatures. And the chemistry is such that you can precipitate the calcium carbonate very easily, but the animals do it. And even plants do it, but the animals do it. How many animals do you know of that make shells out of calcium carbonate? The coral does. Snails do. Clams do. Oysters do. So if you go over there just across the road and look at the ocean bottom, it's just covered with all kinds of shells, bits and pieces of animal remains, the shells that were made of calcium carbonate. Those animals, and there are some plants that have a built-in body mechanism that can take that stuff out of solution and make it into calcium carbonate and make a shell out of it. And then when they die, of course, the shells fall to the bottom. Well, if you take that shell material and put it back together into a rock, it's going to be a limestone. It's going to be a biochemical limestone. And how are you going to know? It's fossiliferous. You can see all the fossil remains in it. So there's an example of a rock, a limestone, that can be either of chemical origin or biochemical origin, simply because it be precipitated purely by chemistry, by warming the water up, or by letting animals and plants do the thing for you. So that would be limestones. The other one I want to talk about, however, is not quite as common in that, and is that silicic acid we talked about, that H4SiO4. Now, the chemistry involved here, I'm not sure anybody really knows for certain, but the chemistry involved, it has to be something on the order of that responsible for the formation of limestones, because we find them intimately associated with each other. But here's the deal. That silicic acid, once it gets into the marine environment, decomposes into silica, SiO2, two waters. In other words, a hydrous mineral. It's a gel, as a matter of fact. It's not even a mineral yet, because it's just a gel. That stuff falls to the bottom, and then it gets rid of the water. In other words, it dehydrates, crystallizes into a thing we call chert. Now, chert is not very, very common. You probably may not have ever heard of it, but there is a form of chert that everybody's heard of, flint. Flint is a form of chert. The difference is it's very pure, very uniform in texture, and very, very strong. It was discovered by paleo people many, many moons ago and used to make tools. It's one of the two major tool makers. The other one is obsidian. But the interesting thing I'd like to point out is that this stuff is not very, very abundant. I won't call it rare, but it's not very common. And so where it was found, the people in the area would have a little cottage industry. They would go out and collect it, and they would make points or scrapers or axes, and at much later time, I might add, arrowheads, because the bow and arrow is a relatively new invention. But anyway, then they would trade it with people for things that they needed, whether it's food or skins or whatever. So there were trails set up throughout the country for commerce. And one of the main agents in this commerce was the transmission of this flint to people who didn't need it or didn't use it or didn't have it. But anyway, some of these trails are still here. And one in particular I always want to point out to my students is the Appalachian Trail that goes all the way from Georgia up to New England. The reason why I bring that up is because most people think the Appalachian Trail was established by the U.S. Park Service. No, the Appalachian Trail was there 1,000 years before the first European ever even faced in this direction. The Native Americans put those things in, and you find those all over the country, all over the country. Okay, so much for that. Now the evaporites. The evaporites would be things like salt. Now, the big environment, of course, you can find salt and sop in places like Playa Lakes, but I'm going to talk about the big site where the big, thick, rich deposits are formed. It's called a sabkha. It's an Arab word, and I've asked my Arab friends, what does it mean? And they say it's a word that's very difficult to translate in English, but the best they could do was mixture. And I think the mixture they were referring to is the mixture of minerals that form when the water evaporates. But here's the scenario. The southern banks or the southern reaches of the Persian Gulf is the typical example of a sabkha. You have a coastal area very flat, very gently sloping to the sea, probably measured in width in tens of miles, long perhaps in hundreds of miles. The waters flood in at high tide, covering this stuff, evaporating as it comes in because of the dry conditions, precipitating out the salt. By the time the tide goes out, there's no water left. So every high tide, there's a thin layer of salt deposited, a thin layer of salt every time. If you do that's twice a day. If you do that for a few million years, you can find a lot of salt accumulating. And then if you bury it under rocks, then you have a layer of salt at depth that you can go down and mine. And that's where most of our salt comes from. Now, one last comment. There's a process now of taking these loose materials, if you will, and turning them into rock. That's called lithification. There's two ways it's done. One way is compaction. This is strictly with shales. Picture mud. What you're going to do with mud, you're simply going to bury it and squeeze it by the overload of the rocks above, and you're going to physically force out the water, and the particles of the clay minerals are going to get closer and closer together and finally stick, and that's basically what compaction is all about. So the formation of shales is a very, very simple process. There's complexities in there, but we won't worry about those. So that's compaction. The other one is the process that acts on all the other kind of rocks, sandstones, limestones, where you got bits and pieces, just sort of spaces between them. Here now we have groundwater moving through. And in the groundwater now are all these bicarbonates, especially calcium bicarbonate in solution. And what happens is these things move through and those minerals precipitate out in the little openings between the grains. Now, that's like putting cement between bricks, you see. Sooner or later, when you fill up enough of those holes, all of a sudden the bits and pieces of quartz, let's say, or limestone start sticking together, and you end up with a rock where before you simply had loose sand or loose fragments of shells. That's called, obviously, cementation. And so with that, we'll end our discussion of sedimentary rocks, and the next topic will be metamorphic rocks.